right? If the density of the object is greater than density of the liquid, then it will sink. But, okay, I'd like to put a star here. You should ensure that the entire volume of liquid displaced is filled with a denser material. Okay, or at least the mean density of the object or average density should be greater than density of the liquid. What I mean is, like last class also we discussed, suppose there's an object like this. Fine. Now, when you immerse something into a liquid, that something, the object that you immerse will have an outer boundary. Okay. Let's mark that boundary in yellow. As of now, the entire volume, okay, which volume? The entire volume of liquid displaced by this object, okay, the entire volume of liquid displaced by this object is filled with a material of density rho naught, which is greater than rho L. Fine. And in that case, it will definitely sink, right? And last class we discussed, if you start creating cavities in this volume, okay, if you create some empty space, or if you ensure that there is some empty space, then there is a chance that the object floats. Okay, even if the material density is more than the density of the liquid, if there is a cavity inside, then there's a chance that it floats. That is how ships float. We had discussed this in the last class. Okay, let's solve one problem based on this. Assume density of a liquid is rho, and the density of this material with which the object is made, let's say it is 3 rho. Okay, hope you're able to see it. Fine. Now, this outer volume that is there, this boundary volume that is there, let it be V. That's the volume that is immersed into the liquid. Fine. Had that entire volume been filled with the same density 3 rho, the object would have gone down, accelerated downward, or sunk into the liquid. But if you create cavity, if you create some empty space, then basically what happens is the object feels lighter. Buoyant force will remain the same, but its weight will decrease. So there's a chance that buoyant force dominates. Okay, there's a chance that it floats or begins to rise. So what I want you all to find out is, if material density is 3 rho and liquid density is rho, calculate the fractional volume of the cavity. Okay, what do we mean by fractional volume of the cavity? Volume of cavity divided by total volume. That is fractional volume. Means how much fraction of the total volume is the cavity. Calculate the fractional volume of the cavity such that the object neither sinks nor floats. Okay, neither sinks nor rises. I think that will be better. So if you release it inside the liquid, it has to stay there itself. Okay, think carefully and solve this. I'll give you all 3 minutes. Now, according to the question, once released, the object should neither sink nor rise. Means the net force on it should become zero. What forces act on this object? When I say object, I mean along with cavity. Okay, the material along with the cavity. Whatever is there in that yellow boundary is what we are calling as object. Okay. So weight should be balanced by buoyant force. How do you express weight of this object? See, had the object been uniform, means had it had the same density everywhere, we could have written density into volume into gravity. But this object, okay, whatever is inside that yellow boundary is not uniform. Some part of it has density 3 rho. Air density is negligible. Okay, you can think of it as massless. Okay, the part of air that is trapped there in that cavity, you can assume it is massless, or you can assume the cavity to be vacuum, nothing present. So how do you express the weight of this object? Its density is 3 rho, but that density 3 rho is only filling a volume of V minus Vc. It's not filling the complete volume. Okay, cavity volume I'm calling as VC. So the volume in which the material is present is only V minus VC. That will contribute to the mass, no? So that volume has to be considered, multiplied with G. So that becomes the weight of the object. Should be equal to buoyant force. How do we express buoyant force? Now this is a non-accelerated container. In that case, buoyant force is equal to weight of liquid displaced. We had done this many times. Density into what is the volume of liquid displaced? That yellow boundary. Okay, whatever is the volume inside that yellow boundary. So total volume multiplied with G. That's all. You just have to rearrange this equation to get the ratio Vc by V. Rho and G get cancelled. Left hand side becomes 3V minus 3Vc is equal to right hand side V. That means 2V is equal to 3Vc. So Vc by V becomes 2 by 3. Okay, vanilla good. So if you keep 2/3 of that object empty, then that object will neither sink nor float. Okay. Now, these questions can be made tougher also. Like here, you were given a question where the net force is 0. You may even be given a question where they ask you what is the fractional volume of the cavity by giving you an acceleration. Okay, like for it to accelerate at this much rate, how much volume should be empty or how much fractional volume should be empty? Such questions can be asked. Okay, in tomorrow's worksheet, you will have problems like that. Now, let's consider the same situation. But before that, tell me this. Uh, let's say 2 meter cube of some substance A weighing 4 kg is mixed with, let's say, 1 meter cube of B, some material B weighing 5 kg. Okay, so 2 meter, these are fine. You can assume them as liquids only. 2 meter cube of liquid A weighing this much. Oh, okay, wait. Doesn't matter whether it's liquids or solids. Okay, 2 meter cube of A weighing this much is mixed with 1 meter cube of B weighing this much. Calculate average density of the composite system. Density is mass by volume. Okay, based on that, you tell me what is the density of this combined system. I'll give you all 1 minute. Solve it quickly. Total mass of the system is 4 plus 5, that is 9 kg. Divided by total volume of the system is 2 plus 1, that is 3 meter cube. So average density becomes 9 by 3, that is 3 kg per meter cube. Now only the first material, if you consider, 4 kg occupies 2 meter cube. So its density will be 4 by 2, 2 kg per meter cube. Only the second material, if you consider, 5 kg occupies 1 meter cube, means its density is 5 kg per meter cube. So basically what you need to understand here is that by mixing a denser, I mean, by mixing a material of higher density and a material of lower density, you can create any amount of density that you want. Okay, or any magnitude of density that you want. You just have to adjust the volumes, okay, or the amounts. Fine. So, okay, let's try one more question. You'll understand better. 3 meter cube of material A of density 2 kg per meter cube is mixed with, let's say, 2 meter cube of density B, sorry, 2 meter cube of material B of density, let's say 4 kg per meter cube. Fine. So we are mixing two different materials, of course, two different amounts of them. Calculate the average density of the mixture. Do this all of you. I'll give you all 2 minutes. Now we need to calculate the average density of this mixture. That is nothing but total mass by total volume. Total volume 3 meter cube plus 5 meter cube, that is, sorry, 3 meter cube plus 2 meter cube, that is 5 meter cube. That's fine. Total mass you need to calculate. Now, density is mass by volume, so mass becomes density into volume. So the mass of the material A is its density multiplied with volume, 2 into 3, that is 6 kg. And mass of the material B, density multiplied with volume, 4 into 2, 8 kg. That's all. Therefore, total mass becomes 14 kg divided by volume is 5. The answer is 2.8 kg per meter cube. Okay. Aishwarya, why were you not able to answer? Where were you stuck? No response. Okay, fine, fine. Let's try another problem now based on this case itself. Suppose there's a liquid whose density is rho and we have two materials. Okay. Let's say density of material 1 is 4 rho. Okay, liquid density, let's take it 2 rho. First material density is 4 rho. Second material density is rho. Now you know 4 rho will sink in 2 rho, but rho will float in 2 rho. Okay, so if you make the object entirely out of this density, it will have a tendency to sink. It will sink. If you make the object entirely out of this density, it will float. But if you combine them both, it could neither sink nor float. That possibility will be there. Okay, so I want you to find out, first case, what is the ratio of volumes in which the materials must be mixed such that the composite mixture neither sinks nor rises. Okay, that's one case. Next case, what is the ratio of masses in which they should be mixed such that the composite object, okay, neither sinks nor rises. Fine. Liquid density is 2 rho, keep that in mind. So the mixture should neither sink nor rise. Okay, for that you find out in what ratio of volumes they should be mixed and in what ratio of masses they should be mixed. Okay, I'll give you all 2 minutes, solve this quickly. Right, for the mixture to neither sink nor rise, the average density after mixing should become equal to that of the liquid, that is 2 rho. Let's first calculate the volume ratio. Let's assume their volumes are V1, V2. Now you know the average density, volume ratio is what you need to calculate. How do you calculate average density? Average density is sum of masses of materials that you take in the mixture divided by the sum of volumes. Okay. How do you get the sum of masses? Density into volume will give you mass. So mass of the first material that you are taking is rho 1 into V1. That is 4 rho V1. That's the mass of first material that you take. Next, second material. Second density into second volume. Rho into V2. Divided by total volume becomes V1 plus V2. From this, you have to find out the ratio of V1 to V2. Now, this average density should become equal to that of the liquid, 2 rho. That's all. After that, it's just a rearrangement of the equation. You get, okay, rho can be cancelled throughout. You get 4V1 plus V2 is equal to 2V1 plus 2V2. Send that 4V1 this side, sorry, 2V1 this side. It becomes 2V1 is equal to V2. That means V1 by V2, the answer is 1:2. The answer to the first part is 1:2. Next, what is the ratio of masses in which they should be mixed? Again, average density is 2 rho itself, that of the liquid. Let their masses be M1 and M2. Then the total mass becomes M1 plus M2 divided by volumes. Now you don't know their volumes. Okay. So what you can do is density is mass by volume. Volume becomes mass by density. So first volume can be taken as M1 by rho 1, that is 4 rho. Second volume can be taken as M2 by rho 2, that is rho. That's all. You just take LCM, rearrange this equation, you will be able to find out the ratio of masses. Vanilla has given the answer as 2:1. Okay, fine. Let's discuss one more situation. This question is quite popular actually. Can any of you tell me the formula for volume of a cone? Suppose its height. Okay, there are many ways to write the volume of a cone actually. Suppose the height and radius of its base are given, h and r. In terms of that, what is the volume of a cone?
So 1 by 3 pi r square h.
1 by 3 pi r square h, correct. Pi r square h becomes the volume of a cylinder, okay, whose radius is r, length is h. Cone's volume will be exactly 1/3 of that. Fine. So suppose there is a cone like this. The height of the cone is h. The radius of its base is r. Okay. And this cone is suspended in the liquid by means of a string. The length of the string inside the liquid is L. Okay. Length of the string inside the liquid. Let me indicate that properly. From here to here is L. Fine. Now, if you are able to suspend the object inside the liquid, it means object is denser than the liquid. Let it be. Now you think of the forces acting on this object. By means of pressure, there will be forces acting on the slant surface. There will be forces acting on the flat base as well. The resultant of all these is what you call buoyant force. We had discussed that before also. We know what is buoyant force, right? I want you to think carefully and solve. Think carefully and find out force acting only on the curved surface of the cone. Try this, all of you. I hope you can understand how the cone is suspended. Its base is horizontal. Okay. So the cone is like placed vertically with its base on the parallel to the ground. Okay. Try this. I'll give you all 3 minutes. Okay. Listen, all of you. These red vectors are the forces exerted by the surrounding liquid on this cone. Okay. Some of them act on the slant surface of the cone. Some of them act on the base of the cone. The resultant of all these is what you call buoyant force. Okay. So you can write a vector equation like this. Buoyant force is the resultant of force acting on the slant surface plus force acting on the base. This is a vector equation. Now see, force acting on the base is in the upward direction. That's fine. On the slant surface, if you observe the forces, okay, they are acting at an angle but in the downward direction. Can one of you tell me what will be the direction of resultant of only those forces acting on the slant surface? What will be the direction of resultant of these forces?
Downward.
It will be in the downward direction. Correct. So force acting on the slant surface is in the downward direction. Force acting on the base is in the upward direction. Their resultant is what you call the buoyant force. Now we know how to express buoyant force on an object. And the base is a flat surface, and since it is parallel to the horizontal, we can easily write the force acting on it by multiplying pressure and area. Once you know those two, you can tell what is the force acting on the slant surface. Okay, the second B stands for the base actually. Right. Therefore, force acting on the slant surface will be the total buoyant force. Don't call it net force. Net force on the cone includes tension, weight. Net force is zero. The cone is suspended there at rest. Okay. So we won't call it net force. We'll just call it total buoyant force. Total buoyant force minus force acting on the base. That will give you force acting on the slant surface. Okay. What is the total buoyant force acting on it? Density of liquid. Okay, that must have been given in the problem. Did I give it or not? Okay, it will depend on that. Density of liquid into total volume of the cone. Pi r square h divided by 3. Because that's the volume of liquid displaced. Density of liquid into volume displaced into g. That is buoyant force. And in which direction is this? Upward. So j cap. Minus force acting on the base. Force acting on the base is pressure on the base multiplied with area because it's a flat surface and uniform pressure. The entire base is at the same depth now from the free surface. What is the depth of the base from the free surface? L plus H. So what will be the pressure on the base? P naught plus rho G. The depth is L plus H. That's the pressure on the base. Multiply that with area of the base. So P naught plus rho G L plus H and multiply that with area of the base pi r square. That is the force acting on the base. And in which direction it is? Upward. That's all. You subtract these two, you will get the force acting on the slant surface. Automatically, this will come out negative. This will be in the minus j cap direction. Okay. So that makes force acting on the slant surfaces point in the downward direction. So see, understand the concept here. You were asked, like an object is immersed in a fluid and you were asked force acting on some part of the object, not completely. And force acting on that some part is very difficult to calculate here. If you want to calculate it separately, it's very difficult to calculate. Why? Because that slant surface of the cone is not at the same depth everywhere. So is not under same pressure everywhere, right? So as you go down, the pressure increases, the forces acting on it will be non-uniform. And the surface is also curved. That makes it even more difficult. You have to take area of an element, take component of that force in the downward direction. That becomes very tedious. Okay, so we have to think of an easier way to solve this problem. So using pressure and calculating force on the slant surface is out of question. That becomes very difficult. So another way to do it is we know what is the total force exerted by the surrounding fluid. That is what we call buoyant force. And only force on the base is easy to calculate. So buoyant force and force on base, if you know, you can find out force on the slant surface. That's the idea we have used here. Right. Next, another question based on buoyant force itself. Now, inside this tank, assume there is a rod. Okay, let's assume rod is made of a different material, a lighter material. And the rod is hinged to the bottom of the tank. It is free to rotate. Okay. And when the angle made with the horizontal or when the angle made with the bottom of the tank is 37 degrees, this rod is released. You can assume length of the rod to be L. I don't know if it is necessary or not, but if necessary, you assume length is L. Area of cross section is A. Okay, think of it as a cylindrical rod. Area of cross section is given, length is given, and you can see it is released in this position. Density of the rod is rho. Okay, density of rod is rho, and density of liquid, take it as 5 rho. So rod is made of a material whose density is less than that of the liquid. So naturally, it will have a tendency to rise up, but it is hinged at one end, so it can't rise up completely, but it can rotate. So I want you to write down expressions for first. Obviously, rotation means torque, angular acceleration, those things will be there. Write torque produced by mg about the axis of rotation. Next, there is buoyant force also acting on it. Torque produced by buoyant force, you write. Once you know these two, like if you can express these two, you can express net torque acting on that object. After that, using mass, moment of inertia. You can write tau is equal to I alpha and get alpha also from their angular acceleration. But do it till here, all of you. I'll give you all 3 minutes exactly. Okay. Visualize the line of action of the force. Magnitude of force multiplied with perpendicular distance. That gives you torque. Okay. Solve quickly. Okay. Uh, can any of you tell me the mass of this rod? Mass is density into
Sir,
volume. Huh.
into
Rho Al. Okay. So rho Al into G will become mg. And what is the line of action of mg? Vertically downward through the center of mass of the object. Through center of gravity, which will be same as center of mass. Okay. So mg acts like this. Fine. We need to express torque produced by mg. Torque is force multiplied with perpendicular distance between the axis and the line of action of the force. The perpendicular distance then becomes this much. The actual distance from there to there is L by 2. Then this will be L by 2 cos 37. Cos 37 is 4 by 5. So 4L by 10 is the perpendicular distance. Therefore, torque produced by mg will be 4 mgl by 10 or 2 mgl by 5. In place of m, you can substitute rho L. Correct only, L by 2 multiplied with 4 by 5. So becomes 4L by 10. Fine. The other force acting on it, other than the force exerted by the pivot, the third force acting on it is buoyant force. Buoyant force acts in the upward direction. Okay, this is a non-accelerated fluid. Buoyant force will act in the upward direction. Can any of you tell me where we should show buoyant force to be acting? We had discussed this in the last class. We talked about something called center of buoyancy. Where is center of buoyancy? Okay, listen. Again, if you remember the basic idea behind buoyant force, you can tell where is center of buoyancy. Buoyant force is or balances the weight of the liquid displaced. Visualize the displaced liquid first. Now, I'm highlighting it in green. This is the liquid that is displaced by the rod. This much volume. Fine. Had that space been filled by the liquid, that liquid's weight would have acted like this. Fine. Buoyant force would have balanced that. So buoyant force would have acted through the center of gravity of the liquid that is displaced. That is what we call a center of buoyancy. We discussed this in the last class. In this case, because the rod is uniform and the liquid is anyway uniform, center of gravity of the rod and center of buoyancy coincide. So both buoyant force and mg will be acting along the same line. How do you express buoyant force? Density of liquid. Density of liquid is how much? 5 rho into volume displaced. Volume displaced is A into L multiplied with G. Okay, that is force. We need torque. So you have to multiply that with the perpendicular distance. Perpendicular distance again is 4L by 10. Okay, they both have the same line of action. So they'll both be having or they'll both be acting at the same perpendicular distance. That's all. You got torque due to mg, you got torque due to buoyant force. Subtract them because they'll be in opposite senses. Mg will be tending to rotate the rod clockwise like this. Buoyant force will tend to rotate the rod anti-clockwise like this. Their torques are in opposite direction. So for net torque, you need to subtract these two. That's all. Okay, that adjustment I think you can do. But remember this idea of center of buoyancy. Okay, you have to imagine liquid in that region. Okay, where would the weight of the liquid have acted? Okay, that means where is the center of gravity of the displaced liquid? There only buoyant force will act. Okay, why? Because the basic idea behind buoyant force is that buoyant force balances the weight of the liquid displaced. Okay, so wherever the weight of the liquid displaced was acting, there only buoyant force will be acting in the opposite direction. Okay, fine. We'll stop it here for today.